Today we're going to introduce another class of transforms that can get around some of the problems that are experienced in the block DCT that we've discussed. And so we're going to start by deriving a transform that's very similar to the cosine transform that we've seen before. Remember, the cosine transform came from the Fourier transform, where we assumed we had some symmetry with the signal. So this one is, we're going to do the same thing, except the symmetry we're going to introduce is a little different. And I'm using this example of x of t over to the left. That doesn't mean that that's what our basis is. It's just showing, demonstrating the symmetry that we would expect, or that's related to this type of transform, and it'll give us a good example. So in this one, we have a signal from 0 to 1, and we do some perhaps rather strange reflections. Of course, from 0 to 1, it remains as it was before, but outside that range, we have this 3 additional reflections of the signal that we're going to get. And so what that looks like, if we started with the x of t above, we get an x tilde of t that looks like this. So it's reflected about the origin, as with our cosine transform. And then it's also reflected beyond that and kind of negated at the same time. So we get something that looks a little bit strange. And this is x of t is on 0, 1, and x tilde of t is on -2 to 2, like that. Okay, so we have even symmetry about t equals 0. And we have odd symmetry around t equals -1 and t equals 1. Like so. So if we represent this using the Fourier series, as we did when we started out our development of the cosine transform, these symmetries tend to get rid of lots of terms from our Fourier representation. And so first off, we're going to get rid of the sine terms because they're odd, and we have even symmetry around t equals 0. In addition, all the coefficients are 0 because of the odd symmetry around plus or minus 1 of a certain form, which in effect, I'm not going to go through it all right now because it's not as essential, but you'll see kind of the impact of it is if we start with the Fourier basis, we end up with, after all the cancellations, psi k of t, these are our basis functions, equal to the square root of 2 cosine k plus 1/2 pi t for positive or non-negative k. So k equals 0, 1, 2, and so forth. Okay, so now if this basis can represent anything on this that has this weird symmetry property that we've defined up above on -2 to 2, then it can obviously represent anything here from 0 to 1. And so we're back where we were before. By coming up with some symmetry, we end up coming up with a new basis that's kind of a special case or subset of the Fourier basis. And these then, psi k of t, form an orthobasis for 0, 1 on L2. So let me just write that more compactly. For L2, 0, 1. So, and this looks a lot like the cosine transforms that we've used. And so this, in fact, is called the Cosine IV transform. So this would be the Cosine IV orthobasis. Like so. Okay. So here are the first four basis functions here. So we have psi 0 of t, psi 1 of t, psi 2 of t, and psi 3 of t. There's also a discrete version. And in that one, we have psi k of n is equal to 2 over n cosine pi over n k plus 1/2 n plus 1/2, and this is for k is equal to 0, 1, on up to n minus 1 for the discrete version. And there's a fast version of this that uses the DCT. Okay, so file that away. We're going to come back and refer to it again a bit later when we develop the lapped transforms. It's going to come in quite handy there. But for right now, it's just an example of another type of basis that we could build up using some symmetry properties.